All right, so now what I want to do is use what we know about the pump beam to actually calculate the average sample temperature or the average temperature on the surface of the sample as a function of frequency. So I had defined this in a previous section, and at the time we were missing an expression for the Hankel transform and Fourier transform of the pump beam. But now we have that, so let's just plug it in. So that has both a spatial component, which turned into a Hankel transform, plus a frequency component now from the Fourier transform that involves an infinite series of delta functions. And then that's multiplied by the point response function times the spatial profile, or at least the Hankel transform of the spatial profile of the sensing beam, all involved in some integral. It creates something a little bit ugly, but we can define a new thing that I'll just call delta T of F. This goes along with Cahill's paper. And basically I'll just pull out all the portions that involve the Hankel transform, which will include the point response function that actually has a Fourier component too. If I do that, then I can write the Fourier transform of the average surface temperature in terms of that delta T that I just defined above, plus that infinite train of pulses. Let me just move this down a little bit so I can put a box around it. We're going to take that, and that thing actually shows up in the Nyquist theorem. Remember that surface temperature is not the surface temperature that is measured on the detector. That is the actual continuous surface temperature. The sensed surface temperature involves what happens when you use the Nyquist theorem, assuming that you are doing discretely sampled moments in time of that average surface temperature. In that case, you use the thing that's in the box as part of another infinite sum that involves some time-delayed stuff. So what I'm going to do next is actually take the boxed thing and shove it into the Nyquist theorem result and see what we get.